Alright, so having established the polar coordinate system in the previous screencast, we're going to move on in our material for Math 1410, and we're going to look at the various elements of a complex number. So we're just going, in this video, we're going to establish some terminology that we will use when we're talking about complex numbers. So I will hope to keep this one short. I'm working on working towards my goal of videos that are 10 minutes or less. We sort of failed with the complex, with the polar coordinates one, but I insist that I am working on it. All right, so here's a picture to refer to. There's some terminology that we're going to introduce. So all of this is referring to a generic complex number, something of the form x plus iy. So we know that this is how we can specify a complex number, and we know that we have this way of visualizing that complex number as a point in the plane, right? So we can draw it like this. You'll see I've drawn it as a little bit of an arrow, starting in a couple of lectures we'll be thinking about vectors, and we'll discuss the fact that we can, if we want to, we can think of a complex number as a vector. So we have earlier introduced the idea of the real and the imaginary parts of a complex number. So we see these guys here, the real part. So the real part is just the x-coordinate. It's the part that doesn't have the I in front of it. The imaginary part, that's the y-coordinate, not including the I. Notice that one thing to kind of keep in mind here is that despite the name, the imaginary part of a complex number is a real number. It's the value of y. It's not I times y, it's just y. The complex conjugate we introduced when we were working on doing division with complex numbers. We saw that it's the same idea as when you introduce a conjugate when you want to rationalize any sort of expression that involves a radical. You multiply top and bottom by the conjugate, you change the sign in front of the radical, and that causes you basically have a difference of squares calculation that works out for you, gets rid of the radical term, and allows you to simplify. Geometrically, you can see that you can interpret the complex conjugate as a reflection because you're changing the sign of the y-coordinates. So changing the sign in the y-coordinate means that you are flipping things across the x-axis. You're taking the mirror image of the original complex number on the other side of the x-axis. So you have a nice way of kind of thinking about the complex conjugate as a reflection. Now, the two new parts that we need to introduce here, because this is going to be how we write our complex numbers in polar coordinates, are the modulus and the argument of a complex number. Now, the modulus, notice that the modulus here, this is just the distance from the origin. So if we think of a complex number as a point in the plane, the complex number is 0 being the location of the origin, then the distance from 0 to any other complex number, we calculate using the distance formula. We get the square root of x squared plus y squared, right? Again, if you want to, you can think in terms of right-angled trigonometry. You've got a little right-angled triangle here. The two sides have length x and y, and so the hypotenuse should have length x squared plus y squared, all under the square root, as Pythagoras tells us. Okay, so that's just the modulus. And be careful when you're working with the modulus. Keep in mind that the square root does not distribute over sums. So the square root of x squared plus y squared, not the same thing as root x squared plus root y squared. If it was, the Pythagorean theorem would be very uninteresting. So there's no, the reason I'm writing the formula like this is because there is no way to simplify that formula. And if you do give in to the temptation to somehow simplify that, you will not be getting the right answer. So keep an eye on that. The argument is this angle theta that is made between the positive x-axis and the ray drawn from the origin to the point z. So it's just the same as when you're trying to define the polar angle when you're dealing with polar coordinates. So notice that if you're thinking in terms of polar coordinates, that in fact the modulus is just r, right? So r is equal to the modulus of z if you're thinking polar coordinates. So the idea is we want to figure out, how do you write down a complex number? Rather than writing it down in this form x plus I times y, we want to figure out how to express a complex number, not in terms of x and y, but in terms of r and theta, in terms of these two values. If you're reading the textbook, I'll mention that in the textbook they mention a little bit that there are kind of two types of argument you might talk about. There's a little a argument, and there's also a capital A argument. This is not something that we need to concern ourselves with. In more advanced courses on complex numbers, you might have to worry about these sorts of things. If you were trying to define complex functions, you have to worry about it. We don't have to worry about it. The two definitions are there because of the ambiguity in the polar angle, the fact that you can always add any multiple of 2 pi, you can subtract a multiple of 2 pi. Generally, the way you resolve this is just by choosing some interval, say from 0 to 2 pi, that you want that argument to live in. But there are cases where you have to be a little bit more general. All right. So let's just do a couple of examples so we can get a feel for things. So let's say z is equal to maybe 3 plus 4i. If that were the case, we know that the real part of z is 3, the imaginary part of z is 4, the conjugate of z is 3 minus 4i. The modulus of z is the square root of 3 squared plus 4 squared, which is the square root of 25, which comes out to be 5. Not the 7 that you would get if you ignore the way that square roots work. The angle, well, again, we mentioned this in the polar coordinates video. We had kind of the same point as a point in the plane. We can write tan theta is equal to 4 over 3, or if we want, we could write theta is equal to arctan of 4 over 3. But that's really about as much as we can do with that, right? We can't express that angle in any sort of simpler way. On the other hand, if we had something like, say, z is equal to minus root 3 plus I, we can deal with this guy as well. Here, the real part of z is equal to minus root 3. The imaginary part of z is equal to 1. Keep in mind that I is the same thing as I times 1. The complex conjugate is minus root 3 minus I. And let me just kind of quickly plot this point. So where is this point? This point is in the second quadrant, right? It's out here. X is negative, Y is positive. We're sitting out there in the third quadrant. We're going to need that angle in a second. What is the modulus? So the modulus of z, square root of minus root 3 squared plus 1 squared. So that's the square root of 3 plus 1. 3 plus 1 is 4, so I get square root of 4, which gives me 2. Now, for the angle, there's a couple of ways that you could try to come up with the angle here. You could say, okay, well, I know that tan theta is equal to y over x, so it's 1 over minus root 3. And then you might say, okay, well, let's see. You probably don't remember your special angle values very well for tan theta, right? I don't. So you might want to say, okay, how do I get the corresponding x and y values? And you might think about, okay, well, if I take the real and the imaginary parts, so what's happening here is that, you know, the modulus is equal to 2, so you've got a point which is sitting on a circle of radius 2. And if you wanted the corresponding point on a circle where the radius was 1, one of the ways you could do that, this point here, which of course will define the same angle, so let's call this point, maybe we'll call it x prime, y prime. So there, r is equal to 1, we're half the distance out. The way you would get there is just divide the real and the imaginary parts by 2. So we'd have x prime is equal to minus root 3 over 2 y prime is equal to 1 over 2. And then either because you've memorized your unit circle or maybe you've printed out a copy and you have it sitting in front of you, you can look things up and you can say, okay, I know that theta in this case should be 5 pi over 6, and that will give me the right value in this case.